Okay, can you see it?
Yes.
Oh, good. Oh, great, great, great. I see many friends, so I'm very happy to give this talk. I thank Alessandro Strumi and Michele Redi for inviting me. How to make this thing very much smaller, this stupid thing. Anyway, so this is the title of my talk, and this is the plan of the talk. So after very brief comments on chiral gauge theory in general, motivation, and some comments on earlier and more recent studies on these theories, I go to the main topics of this talk, which is the application of these generalized Hooft mixed anomalies to study the phases of chiral gauge theories. So why do we study, why are we interested in chiral gauge theories? The basic point, I think, is that we do live in a world with chiral structure. In particular, at the subnuclear level, our microscopic world is very precisely described by the standard model, SU3 and Grashow-Weinberg-Sam SU1 theory. And this, of course, is a chiral theory. Let me make it smaller. Yeah. Okay. The basic reason for such a chiral structure, I think, lies in the structure or symmetry of the world we live in. That is that the Lorentz group are the smallest representations, which are spin 1/2 multiplet of definite chirality. Now, these are a weakly coupled theory and a consistent imperturbation theory. In other words, they are perfectly reasonable or good theories, as long as they are considered to be some sort of low energy effective actions. But as such, they leave, as you know, many mysteries, many unknown features of the model, mass spectra, family structure, neutrino, etc., etc. In particular, the origin of the electroweak symmetry breaking, naturalness, and so on. Now, a great amount of work has been done in the last 40 years, almost half centuries, on the strongly coupled asymptotically free gauge theories. One of the main results being on QCD, SU3 and Mills with quarks, and N equal to supersymmetric gauge theories. Almost a quarter of century of work on this theory has revealed really deep insights on the infrared fixed point conformal theories, global symmetry breaking, confinement, and the relation among them. But they all refer to vector-like gauge theories. At the same time, surprisingly little is known today about strongly coupled asymptotically free chiral gauge theories. So I take this as a challenge for theorists. Understand them. We want to understand them better. So it may be a futile academic exercises, or maybe nature is making use of them in a so far unknown way to us. This does not mean that there has not been many interesting, important studies on these theories. So here is just a partial list of references. You know, some are very well known and some a little bit less known, but they all introduced interesting ideas and hypotheses such as tumbling, complementarity, and then the Hooft anomaly matching constraints, ACS criterion, A theorem, large N, and so on. But perhaps it's fair to say that no truly significant progress has been made so far on chiral gauge theories. So, motivated by such a consideration, we recently revisited the dynamics of chiral gauge theories, which are all asymptotically free, no mass parameters, potential, no theta angle, unique vacuum. And we asked these questions. And the models we studied are a sort of wide class of models with fermions with a number of symmetric representation, or a number of fermions in anti-symmetric representation like this, and a number of fermions, all wild fermions, either in the fundamental or anti-fundamental representations. And the number of the latter, of course, is fixed by the condition that the theory be anomaly free. And we asked these questions, and I do not think I have time to go through the analysis. So let me just list perhaps the lessons we learn from this kind of study. And basically, what happens is that Hooft anomaly matching conditions, together with other basic requirements, are so severe that very often we find it very difficult to find the solutions simply. And what we found out is that a partial hypothesis of partial color flavor locking due to some bifermion condensates, together with the idea of dynamical Higgs, and partial dynamical abelianization, combined together very often helps us to find, in general, non-unique solutions of these constraints. So maybe these are the lessons we learned, not very much. And in particular, we really need of more powerful theoretical argument. It's really badly felt. So this brings us to our main subject of the talk, which is application of generalized Hooft anomalies and the phases of chiral symmetry, the phases of chiral gauge theories. And this is based on this work with Bolognesi and Luzio. Now, in the first part, we study the consequences of gauging exact one-form ZK center symmetries in several simple SUN gauge theories with chiral or vector-like fermions, where K is a divisor of N. Indeed, this part of the talk overlaps considerably with what Eric talked about already, so I'll be quite brief. Models we studied are those with fermions in a self-adjoint anti-symmetric single column representation like this for SU6, or adjoint QCD Eric talked about, or QCD with pairs of quarks in either symmetric or anti-symmetric second-rank tensor representations. And models with fermions in a representation in a number of symmetric representation fermions and the number of anti-symmetric representations, with where K is such that N minus 4 over K and N plus 4 over K are both integers. And this leaves still plenty of space for different choices for N and K, leaving asymptotically free conditions, such as SU36 model with one fermion in symmetric and 5 fermions in anti-symmetric, and so on. Now, I should go to the result, in fact, but let me just go through a couple of slides quickly. This partially overlaps with Eric's talks, which I will go very, very quickly. And partially, we need some formulas specific needed for this talk. So the first ingredient of this new approaches is that to generalize the concept of symmetry from zero-form standard zero-form symmetry acting on local operators to K-form symmetries like acting on line surface and operators. And this is all the idea of center symmetry is well known, so I can basically skip here. Let me only remember that higher form symmetries are all abelian, and this will be important later. The next ingredient is the idea of gauging the one-form discrete ZM symmetry. And again, this has been discussed quite well by Eric. So let me just remember a couple of things. One is that gauging a discrete symmetry is a sort of unfamiliar concept for perhaps some people in view of the ordinary idea of gauging of a continuous symmetry. But here it simply means to identify the configurations connected by it and eliminating the double counting. And to do so, we introduce the UN gauge field instead of SUN gauge field. Here we use very, very compact notation of differential form notation like this. For gauge fields, instead of writing T, R, B, A mu, R, dx mu, we just write it as simply as A. TR is the generator appropriate for fermium under consideration. And then introduce a UN gauge field like this. We introduce a pair of one form and two form gauge fields. Let me call it B2 and B1, which satisfy this kind of constraints. And then impose the one form gauge invariance, which is written here. And this effectively converts the gauge group from SUN to SUN over ZN, otherwise called PSU gauge theory. And this procedure has a dramatic consequence of converting the topological invariance, which is this one. So this is an integral over sigma 4, four-dimensional spacetime of F mu nu dual. Let me remember that this is not F mu nu square, but F mu nu dual, which are usually in the usual standard quantization, which takes integer values, integer instant numbers, and they are converted to these combinations, which take fractional topological charge. And this is related to fractional magnetic flux discussed by Eric. And the last thing which we should discuss here is that idea of gauging exact one form ZK symmetry in the SUN model, where K is a divisor of N. And this is also has been discussed by Eric. So I'll be, again, quite quick. So again, we introduce pair of B fields, now which satisfy this constraint here, K instead of N. And we impose invariance under one form transformation like this. And this tells me that I have to replace usual F mu nu gauge field tensor by this kind of combination, which is invariant under this one. Fermium kinetic term is written like this. So this is a standard gauge coupling, gauge field coupling to the fermium. NR is annuality appropriate for this fermium. And A psi is an external gauge field, which I introduce to describe the U1 psi transformation. And the standard U psi 1 anomaly is given by this familiar expression, where this is an integral of FF dual. 2TR is a Dinky index. So this leads to the familiar result that some subgroup, which is a Z of 2TR of U1 psi remains non-anomalous. Now, when these B fields are introduced, so we gauge this one form ZK symmetry. This topological invariant, which appear here, is replaced by this combination. And this combination in general is fractional. And this is leads to non-trivial result in this series. So we briefly reviewed this. So this allows me to discuss the result on these theories. So this has been almost touched by Eric again. So I just skip. It's interesting that to discuss the SUN generalization of this model. And this was discussed by Yamaguchi. With SUN theory with a single wire fermion in this kind of representation. Now, for n equal 4, we find that no new mixed anomalies arise. For n equal 4L, there is some non-trivial mixed anomaly, and therefore the unbroken subgroup associated to this fermion, which is Z of 2TR, which is respected by standard instanton, is broken to smaller discrete symmetry. And similarly for n equal 2L plus 2, but this surviving discrete group is different. And therefore, this implies some kind of condensate to form in the infrared. And this has been discussed by Popitz. And in the case of this kind of model, we find again that one form Z2 gauging introduces further breaking of discrete chiral symmetry. This model, and in this case, you can check that this kind of result, anomaly, mixed anomaly, implies that at least two of the condensates must form in the infrared. Now, there are some interesting systematics to discuss, but I will skip this one because this is a little bit technical. And this brings to the second part of the main discussion of this talk, which has just appeared in the archive. Here we study the consequences of gauging the one form ZN center symmetry in some simple SU1 gauge series with chiral fermions, including those in the fundamental representation. Now, here is something new, that is that ordinarily, fermions, presence of the fermions in the fundamental representation would simply break the center symmetry and preventing us from applying these interesting new techniques to the system. The point is that we can use color flavor locked ZN symmetry to do the gauging of this kind of symmetry. So this is what we are going to do. The models we discussed are quite simple ones. One is we call the psi-eta model, which is the simplest of the so-called Bars-Yankelovich models. The SUN model with a single fermion in a symmetric representation and n plus 4 fermions in the anti-fundamental representation. And this model is quite similar. Let me discuss only this psi-eta model, which is this model we just mentioned. And this model has been studied several times in earlier. Symmetry group is SUN plus 4 associated with these fermions, and U1 psi-eta, which is a linear some combination between two U1s, which remains anomaly free. Now, this model is particularly interesting because the conventional Hooft anomaly matching constraints allow both chirally symmetric confining vacuum with no condensates forming and with massless composite fermions, candidate massless composite fermions given by this kind of objects, where, which are anti-symmetric in flavor index AB. And another possible vacuum is what we call color flavor locked dynamical Higgs phase, where bifermion condensates of this form is generated by the system, and that generates a number of massless baryons and number of Nambu-Goldstone bosons. So these are just the tables of these fermions with quantum numbers. To actually looking at these tables and these quantum numbers, it is really quite trivial to check all these statements that this satisfies all anomaly triangles associated with U1 times SUN plus 4. Now we wish to find out, however, if the generalized Hooft mixed anomaly matchings gives a stronger constraint on this system. First of all, we have to be more careful about the symmetry. The true symmetry group of the system turns out to be this one for n equal even, and not the naive formula like this, naive SUN equals 1. And this is because there is some kind of double counting in this traditional symmetry group. And we have to mod out. And this turns out to be Zn and Zn plus 4. Zn symmetry is included, which is a diagonal group, diagonal combination between Zn inside SUN and the Zn factor included in the U psi U1 and Z2F. Z2 is a fermium parity symmetry in which psi and eta change sign. Now, this is the central issue of the central point of this discussion. So let me be a little bit more careful. Zn transforms psi and eta like this. You remember that psi is in the symmetric tensor representation. Eta is an anti-fundamental representation. So Zn, color Zn factor acts like this. Whereas Zn fermium parity transformation and the U1 psi eta with an appropriate angle acts like this, and this is actually identical to this. Okay, this you just look in there. And actually this can be understood as a generalized co-cycle condition in the triple overlapping region Eric was talking about. So generating SUN over Zn gauge group, basically. Now, to study the anomalies associated to Z2 symmetry, we introduce the external gauge fields, U1 psi, psi eta, just U1 gauge fields. A21 is a formally continuous, again, U1 type gauge fields describing Z2 symmetry. AF is just SUN plus 4 gauge field. Small a is a SUN gauge field, sorry. And again, pair of B fields satisfying these constraints. And this B field has a flux over closed two-dimensional surfaces, which are subspace of our space-time, which is fractional in general. And then we impose the invariance under this new one-form transformations, under which not only color and SUN gauge fields, but also Z2 and U1 gauge fields, transform. And this actually combined transformation is nothing but the reflection of this such a symmetry we discussed about. Okay, and then we write down the fermium kinetic terms, and then we start to computing. And before computing anomalies, we have to replace each of these terms with form invariant under all these things here, all these one-form gauge transformations. And this brings me to write down the invariant tensors fed by fermions. So these are just gauge due to gauge field, appropriate for symmetric representation fermion. And these symbols are almost really obvious. And this is a U1 coupling. And this is a coupling to Z2 external gauge field, A2. And this, and this. These are just fixed by the charges of these fields. And then we start to compute mixed anomalies. And here as a result, but let me just flash a couple of slides to show how this formula look like. So we used Stora-Zumino descent procedure starting from 6D anomaly functionals. But really, we can do or go through this calculation using Fujikawa, staying only in 4 dimensions. Nonetheless, this approach has several merits, as we can check. Now, this formula looks rather horrible, but actually, after deep respirations, you start to see that each of these terms have really transparent meaning. For instance, this term is gauge SUN gauge anomalies. Okay, this is made one form gauge invariant form, but this is basically F mu to cube. And same for eta. Yeah. But in the sum, of course, this term disappears because the system is anomaly free. So this coefficient from eta and coefficient psi cancel. And similarly, for instance, this is a U1 psi cube. So there is this coefficient for this coefficient from eta. The sum is given by this coefficient, this complicated coefficient. But then this is equal to the contribution from baryons, like this. So this is concerns the thing we already said, that in this system, standard U1 cube or U1 SUN plus 4 squares, U1, and so on, all these traditional Hooft anomalies are matched by these massless baryons, candidate baryons of this confining vacuum. So really, these formulas contain all this information in a very, very transparent fashion. And then to compute the anomalies, what we do, we find out the total derivative form containing, however, discrete anomaly, discrete gauge field A2, and then we go to find the 5D boundary with Zumino-Witten action, which looks like this, and then consider the variation of this A2 field, variation corresponding to this. So this corresponds to precisely to psi going to minus psi and eta going to minus eta due to this factor 2, factor 1/2. And now, then you go to pick up the coefficient of this variation. And, this is, again, total derivative. And this is a well-known thing that all this Witten action gives anomaly variations which are present only in the boundary 4D space-time. And this corresponds to what we call anomalies in the 4D standard theory, anomaly inflow. So the results. Now, the mixed Z2 Zn square anomaly. And by computing just collecting all these terms of the same form like this, from different pieces from contribution from psi and eta, we get to just one. Now, it means that under psi going to minus psi or eta and going minus psi, the partition function changes sign. And therefore, there's a Z2 anomaly. In comparison, without gauging the one-form symmetry, so by setting all B equal to 0, we would have found simply the standard instanton term. Of course, I forgot to say that this instanton term is also present, but it is not very interesting. And this is an interesting term coming from this P square flux. We would have found, without gauging the one form Gn symmetry, we would have found simply this one with coefficient 2, and then this is a standard integer instanton numbers times plus minus pi. And then we see that the Z2 anomaly is actually absent. In the infrared, in the presence of this B field, we find that Z2 anomaly are absent. simply various contributions like this simply cancel out in the case of baryon contributions, assuming the chirally symmetric vacuum. And therefore, mixed Z2 Gn square Hooft anomalies does not match. And therefore, chirally symmetric vacuum is inconsistent. And other anomalies leads to the same contribution, same conclusions. So that will be really the end of my talk, but let me just make several reflections and discussions on these calculations. Anyway, conclusion that mixed Z2 Gn square anomaly does not match between ultraviolet and infrared, and therefore chirally symmetric confining vacuum considered earlier cannot be the correct vacuum of the theory. Vice versa, there are no difficulties in the dynamical Higgs phase characterized by such bifermium condensates, which is more likely to be the correct vacuum of the theory. Now, we introduce several conceptual new extensions in this analysis. This we discussed already. Mixed anomaly involving this discrete symmetry. And the fact that the roles of U1 and the Z2 symmetries and their external gauge fields are formally similar. And both A and A2 transform non-trivially under the one-form gauge transformations, which we checked like this. See? Both anomalies are affected by two-form gauge fields. However, there is an important difference with anomalies involving only continuous symmetries like this, and the one which involves Z2 symmetry. We already noted that in these cases, anomaly matching was valid before the gauging of one-form center symmetry. And this is because the coefficient of anomaly functionals were equal in the ultraviolet and the infrared, and therefore they continue to be matched after the replacement automatically. And this is not so for anomalies involving discrete Z2 anomaly. Before the gauging of the one-form gauge center symmetry, the absence of the anomaly or anomaly matching was guaranteed not by the equality of the coefficients, but by the equality of coefficient modulo 2 and by the integer instanton numbers. And therefore, discrete Z2 anomaly may arise after the gauging the one-form Gn symmetry, which introduce fractional topological charge, as we saw, and may ruin the ultraviolet infrared matching. Our calculations show that it indeed does. By the way, it is interesting that the result we got C=1 was the only meaningful and non-trivial answer. Because in this case, if we got as coefficient any fractional number like 1/2, 1n, it would have been just nonsense. Either we made calculation mistakes or the construction was wrong, or both. Vice versa, if we got any even integer number, okay, that would have been sort of trivial. Well, it's okay, you can do that, but you don't get anything. At the same time, the fact that we got C=1 does not, of course, guarantee in itself that everything was okay. So this is my last slide. Our result is formally similar to the mixed anomaly found earlier by this in this beautiful paper by Gayot, Kapustin, Komagowski, Zyberg, and other papers found in the pure SU and Yamils at theta equal pi. But the way the failure of the Hooft matching manifests itself in the infrared is different. In that case, on pure SU1 Yamils at theta equal pi, CP is spontaneously broken by doubly degenerate vacuum for n not too small, let's say. And CP is broken a la Lie spontaneously, and then this sort of take care of the failure of matching of mixed anomalies. In our case, the failure of the anomalies of mixed anomalies does not mean that Z2 is spontaneously broken. Z2 is a space 2 pi rotation. But U psi 1 is spontaneously broken, and therefore Gn itself is broken. So this is the conclusion again. This we already said. Thank you. So this is the end of my talk.
Okay. Thank you very much for a nice talk.
Thank you. And this took more time to do.
So we have a couple of minutes for questions.
Can I ask one question?
Yes.
Does this improved understanding of the symmetries resolve this puzzle about the model with the anti-symmetric fermion, where the Wess-Zumino-Witten term did not reproduce the right skyrmions?
I don't know the answer. No, I don't know. Didn't study that question. Which model is it exactly?
It's the model that Stefano Bolognesi looked at a little bit before his papers, but
well, he didn't tell me about. we did this work together. But I see. No, we should discuss with him.
Thank you.
Thank you.
More questions? So I have a question. So
yes.
So for this consideration, is it important whether the theta angle is physical or not?
Theta angle is?
So your examples of theta angle was not physical. Instead, pure Yang-Mills theta is physical. So does it play a role or not?
Does it?
Does it play a role in these considerations or?
Let me see. We have always a theory with chiral fermions, which are massless, and the theta can be always set to 0. So I don't think theta term is relevant in these models. No. Yeah.
Okay. Any other questions? So if not, thanks everybody.
Okay, thanks. Thank you.
See you next.